Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this session we'll be talking on the angular momentum principle. This is the part 1 of the lecture series. Primarily in the first 1 or 2 modules we'll be taking a bit of digression and discussing about the moment of inertia of some of the known objects, which will help us to set up the rigid body dynamics or analyze the rigid body dynamics of these objects. Okay, so as I just mentioned, the topic that we are discussing now is the angular momentum principle. This is part 1 of the series, and we begin our discussion with the basic example of what is center of mass. So center of mass of the system. So suppose a system S of particles P1, P2, Pn with masses m1, m2, mn, and suppose their corresponding position vectors are ri's, and with position vectors r1, r2 and rn, and respectively. So these are the respective position vectors, and the Cm of S is a point in space, whose position vector r is given by summation mi ri by summation mi. So that's my center of mass, and I call this, we can rewrite this equation as summation mi ri by capital M, right? So that's my center of mass. So this question we have to first, so we are trying to answer two things. One is how to find center of mass of an object, and the second in this module is how to find the moment of inertia. So to begin with, to find center of mass, let me first discuss some of the quick tricks or the rules through which we can immediately find the center of mass given some symmetrical objects, right? So what we are discussing is finding center of mass by symmetry. Okay, so rule 1, if the body has reflective symmetry, on the plane, then the center of mass lies on the plane. Okay, suppose we are talking about let's say in a circle or a semicircle, we know that there is a reflective symmetry about a circle with the diameter on the x-axis has a reflective symmetry about the y-axis. So in this case, the rule 1 says that the center of mass lies on the plane of the circle, right? So that's the example. So then the second rule says that if the body if the body has rotational symmetry about an axis, then the center of mass lies on the axis. Okay, I go back for this rule again. I refer to the same example. If we suppose have a semicircle with the radius or the diameter on the x-axis, it has a reflective symmetry about the y-axis. So this second rule says that the center of mass is going to lie about the y-axis, right? Okay, so the example that I have, the written examples that I have are, for example, the example of a cylinder. So a uniform cylinder, let's say a uniform cylinder occupying region x square plus y square is less than equal to a square and minus b, right, has reflective symmetry. On the plane z is equal to 0 and a rotational symmetry about the z axis. So we have a uniform cylinder where, well, so let's say we have a uniform cylinder which the cylinder is kept with its circular part on the xy plane or parallel to the xy plane, and it's parallel to the z axis, and it's given that it has a reflective symmetry about the z axis, so about the plane z is equal to 0, and it has a reflective symmetry about the plane z is equal to 0, and it has also a rotational symmetry about the z axis. So we expect that the center of mass of this particular cylinder is going to lie on the intersection of z is equal to 0 and the z axis, right? So the intersection of z is equal to 0 plane with the z axis is going to be the origin, right? So that's where the center of mass lies for this cylinder. Okay, so let's complete this statement. The center of mass lies on the intersection of the axis and the plane, right? So this is the origin of the cylinder. This is the origin of the axis here. Okay, the other example that I have is that of the equilateral triangle, right? In equilateral triangle, we expect, intuition says we expect that the center of mass should lie on the centroid, right? And certainly that is the case because equilateral triangle also has a reflective symmetry about any two sides, and also it has a rotational symmetry about any two sides. So when we do the same exercise for all three sides, we come to the point that the center of mass lies on the centroid. Okay, so the second example, an equilateral triangle has rotational symmetry about its three medians, so which means that G must lie at the intersection of the medians. G must lie at the intersection of the medians, right? And that's it. Okay, so that is what we have. So let's look at another example, a slightly more complex example. So as I said, let's go back to looking at the semicircle. So the semicircle having its radius along the x-axis, right? And we saw that it has a reflective symmetry about the y-axis and also a rotational symmetry, which means that the center of mass will lie on the y-axis, and we can find it by, to actually find the y coordinate of the center of mass, we need to do a little bit of calculations, which I'll see. So the problem says find the center of mass of a uniform semicircular lamina, right? So center of mass of a uniform semicircular lamina, and the problem says that the lamina has a rotational symmetry about the y-axis, right? It has a rotational symmetry about the y-axis, and the center of mass is, in this case, of course, is going to be 0, y. All we have to do is to find this y coordinate. So the symmetry has reduced our problem. Instead of finding two coordinates, we just have to find the y coordinate, because the x coordinate is 0 by symmetry. So lies on the y-axis. And the formula, I think this is the formula for center of mass has already been given earlier. The formula clearly says that the center of mass is given by, we want to just find the y coordinate of the center of mass. So this is going to be summation mi yi divided by m, right? And now we are talking about a smooth object. We can replace this summation with an integral so that we have a continuous mass distribution, and that is going to be integral m times dA times y by m times pi a square by 2, right? And this is the dA is r dr d theta. So what we get is that this integral is, we can now remember, we are talking about integration over a plane, over the circle, right? So this is a 2D integral. So this integration has is a double integral. So the double integral will have what have we got? The double integral will have the integration over r. So r is between 0 to a, and theta is between 0 to 2 pi, and then this was this was per unit area, the mass per unit area. So we multiplied with total area, and now what we get is, after substituting everything, so r dr d theta times y is, in this case, y is r sine theta. So we are changing everything in polar coordinates, so r sine theta, and divided by pi a square by 2, right? And what have we got here? So y is 2 by pi a square, double integral r from 0 to a, theta from 0 to 2 pi, and r square sine square theta dr d theta, and we see that this is 4a by 3 pi, right? And we get that this is roughly 0.2424a, which is roughly about half the distance. So not exactly half the distance. So what I want to say is that the answer itself is non-trivial, right? We cannot just conclude that not only the center of mass lies on the y-axis, but it is also half the distance. That is not true. So the final answer is non-trivial, but at least the symmetry has simplified our problem. Okay, so then here is one more example. We can extend this first example from semicircle to a hemisphere. So the problem says find the center of mass of a uniform solid hemisphere. And of course hemisphere has has a reflective symmetry about, let's say, the on the xy plane, and also it has a rotational symmetry about the y axis. So sorry, rotational symmetry about the z axis, right? So if we properly draw the diagram, so we have x, y and z. So we have the following. So hemisphere, so it has a rotational and a reflective symmetry about the z-axis, which means that the final center of mass will lie along the z-axis. So all we have to do is to find the z coordinate of the system. So z is 1 over m times integral. Now this time, remember, we are talking about a solid object, so we need to talk about an integral which is triple integral, because we are this is a 3D object we are considering. So we have integral m dv, that's the mass. Let's say this capital M is the mass per unit volume. So m dv times z divided by the volume of the hemisphere, 2 by 3 pi a cube, and times 1 over m, and we see that dv is r square sine theta d theta d phi dr, right? And r is from 0 to a, and theta is from 0 to pi by 2, and phi is from 0 to 2 pi. Okay, so that that will, we can do this integration, and quickly we arrive at the fact that the answer is 3a by 8. Again, the answer is non-trivial. It's not exactly half distance from the xy plane. So that's what I wanted to emphasize. The eventual answer is non-trivial. So then the other concept I want to introduce in this module is the so-called moment of inertia. So suppose we have a system of particle, we talk about the moment of inertia of this system. So in future, I am going to refer to moment of inertia as MOI, right? So moment of inertia of a system S about an axis CD is defined by ICD equal to summation mi pi square, right? So pi is given by pi's are the perpendicular distance. So let us say we are talking about an object and we want to find the moment of inertia. So the moment we want to find this quantity, we have to define the axis. See, moment of inertia has the same idea as that of a mass for a rotating body. So when we are talking about a rotating body, we need to talk about an axis, and from there we can talk the concept of moment of inertia. So the moment of inertia is defined as summation mi pi square, where pi is the perpendicular distance of the object with mass mi from the axis. Okay. Axis, right? So let's call this axis as axis CD. So axis CD. So we talk about, let's say, pi's mi, the object pi of size mass mi is located at a distance small pi. So that's the pi we are talking about, the perpendicular distance, right? Okay, so then what we have is that let's say let's try and quickly find some examples. So one example is find the moment of inertia of a uniform rod of mass m and length 2a about an axis through its center and perpendicular to its length. Right, so we want to find the moment of inertia of a uniform rod of mass m and length 2a about an axis through its center and perpendicular to its length. So, let us see what axis we are talking about. Here is the rod, the diagram, and here is the axis we are talking about, which is perpendicular to the length of the rod. Right, so axis which is through its center and perpendicular to its length. So, to find the moment of inertia, so we need to, so remember this rod is just a 1D object. So now if we want about to discuss the mass distribution, we need to talk about the concept of mass per unit length. See, for 1D it is mass per unit length, the mass distribution. For 2D object we have mass distribution as mass per unit area, and for 3D it's mass per unit volume. So here the mass per unit area will be dm. The infinitesimal mass per unit area will be total mass m times dx divided by length, which is 2a. The rod length is 2a, and at any given, for any given point on the rod, the perpendicular distance from the axis of rotation, let's say CD, the axis of rotation will be x. Right? So if we want to find this moment of inertia, this will be summation mi pi square, right? And then we change this to integral, so this becomes integral dm times x square. So that's my moment of inertia, and dm, so what we have is, so dm times x square. So this integral becomes integral x square times dm. So dm is m times dx by 2a, and let's say this, since this axis is passing through the center, the integration will be from minus a to a, because the axis is passing through the center. And what we have is that this is m times integral from minus a to a x square dx by 2a. Right, and what we have is that this is m times, the answer is m a square by 3 this time. Sorry, 3. We integrate x square dx, we get a 1 by 3. So, so that's for the rod. Let us look at one more example, and then I'm not going to do each and every such symmetric body case, but we will tabulate the result later on. So here is one more example. So the next example says find the moment of inertia of a circular disc of mass m and radius a. About its axis of symmetry. Right? Moment of inertia of a circular disc of mass m and radius a about its axis of symmetry. And then let's see. So the moment of inertia of the disc will be, so this time we are talking about a 2D object, so we have to talk about mass distribution per unit area. So here dm will be m times dA by pi a square, where a is the radius. So again, axis of symmetry is the axis which is passing through the center and of course perpendicular to the disc. Right? So this is what we have. So CD. Okay, so dm is this, and now moment of inertia will be integral dm times let's say at any given distance it is r. So it will be r square. Right? So now this integration is expanded into the double integral. So we have m times dA. It's a dA in polar coordinate can be reduced as r dr d theta. So that's my dA, and divided by pi a square, and we have what have we got? Pi a square integral. So r is over from 0 to a, and theta is from 0 to 2 pi, and we have that we integrate everything and we see that the final answer comes out to be, well, I think we have missed an r square. So we also have a r square sitting here. The final answer comes out to be ma square by 2. Okay, similarly, if we want to find that of a solid sphere, this time we will be involving triple integral because we will have mass per unit volume, and the integration will involve integration over the solid angles theta and phi. And once we do that, we are going to arrive at the answer that the moment of inertia of a solid sphere is 2 by 5 ma square. Okay, so enough of all these simple trivial examples. Let us now tabulate all the results for these for these known objects or these polygonal objects, right? So the list that we have is, I've just compiled a short list. So moment of inertia list. So suppose we have a thin rod of length 2a, thin rod of length 2a, and then in that case we get that we have already seen the answer is ma square by 3, right? So that's my moment of inertia. Let's say this is my regular axis, the axis of symmetry. Then how about a circular hoop? This time it's a, so what exactly is circular hoop? This is of mass m and radius a. So circular hoop is a hollow circle. It only has a perimeter. So this will again involve a 1D integration because this will be mass. The mass distribution is only mass per unit length along the perimeter, right? So the answer is, again, along the regular axis of symmetry, we see that this is going to be, ICD is going to be ma square. We can do the integration. This is going to be 1D integral. Then similarly, suppose we have a circular disc of mass m and radius a. Mass m and radius a, and we see that the disc becomes this answer again along the regular axis of symmetry was ICD is half m a square, right? Interestingly, we see that the hollow objects have more moment of inertia than the solid objects. We will see a similar setup for even the 3D sphere case. Let me continue this list. The fourth example I have is that of the solid sphere. We have also found this. So solid sphere, mass m and radius a, and we see that ICD is 2 by 5 ma square. Okay, we have just found this. And then the fifth point in this list is spherical shell. So mass m and radius a, and in this case the regular axis, again the axis passing through the center and along one of the diameters, the regular axis comes out to be 2 by 3 ma square. Again, we note that the moment of inertia of the thin object or the hollow object is more than the moment of inertia of the solid object, right? And then that of the circular cylinder, the mass m, radius a, and the length 2b, we see that so we are talking about this time, so the cylinder will be mass m, radius a. So the radius is a and the length is 2b. And we are talking about along an axis which is not perpendicular to an axis which is perpendicular to the lateral surface of the cylinder. So this time my ICD is the axis which is perpendicular to the lateral surface of the cylinder, and in this case my moment of inertia comes out to be 1/4 ma square plus 1/3 mb square. Okay. This last result of the cylinder has come out from the perpendicular axis theorem, which we will reveal shortly. So let us wrap up this discussion on moment of inertia. And before we leave this topic, let me give few tricks to find the moment of inertia. Okay, so the point we are discussing is useful tricks to find moment of inertia. Okay, so the first trick is the moment of inertia of a body is unaltered if its masses were moved. Moment of inertia is unaltered if its masses of bodies are moved in any manner parallel to a specified axis, then the trick says that the moment of inertia is unaltered. So to understand this statement, we just see an example. Say, for example, suppose you are given a cylinder, right? Cylinder, right? And we want to calculate the moment of inertia of the cylinder about its regular axis of symmetry, that is parallel to its lateral surface, right? And the way to do that is, suppose we alter the cylinder, we squash the cylinder to a disc. So that way we have altered the distribution of masses of the cylinder. This trick says that the moment of inertia of this disc about the same axis is going to be the moment of inertia of the cylinder about the same axis. So that's what this rule says, right? So let me write what I just said. So the moment of inertia is unaltered if it is squashed into a lamina perpendicular to a specified axis. If it is squashed into a lamina perpendicular to a specified axis, right? So as I just said, the moment of inertia of a cylinder about the natural axis, about the axis of symmetry, is identically equal to the moment of inertia of the disc about the same axis, right? And about the axis of symmetry. So that's one. The second, for example, the moment of inertia of a plate is the moment of inertia of a rod. So the moment of inertia of a rectangular plate is the same about, let's say, about the x-axis, right? So moment of inertia of the plate about the x-axis is the same as the moment of inertia of a rod of the same mass and length about the x-axis, about the same axis, right? So suppose a plate is squashed to become a rod. Although the plate is a 2D object, the rod is a 1D object, but so eventually we see that the mass distribution has changed. So this trick says that the moment of inertia is unaltered if we look at the same axis of rotation. Okay, so then so what have we got? Well, I needed to say a bit. This is the rectangular plate. The axis here of the plate passes through the center, right? Because when we are squashing, That's what we are saying. The axis passes through the center, okay, of the plate here. Okay. The second trick of finding the moment of inertia, I think we have 1 or 2 minutes, so let us wrap up by saying the second trick. It says that suppose the moment of inertia of an object is found, right? Then the moment of inertia of a small part of the object, right? Suppose we have been given some object, let's say a solid sphere, and we cut this sphere, or we cut this object into equal parts, right? So we cut them into equal number of parts, which makes equal contribution to the moment of inertia. Then the moment of inertia of each of these parts will be the same as the moment of inertia of the original body, except that the mass of this part will be the mass of whatever the part is, right? So we have to replace the mass of the body with the mass of the part, right? But the expression of the moment of inertia is identically the same. That's what this trick says. So I think I'm all out of time here, and in the next module we'll follow this trick, and using these two tricks we are going to find the moment of inertia. And further we are going to look at two important theorems which helps us to calculate the moment of inertia at other axis of rotation. Thank you so far for listening.